For years, lasers have been a hallmark of science fiction, yet much of our technology today depends on them. Range-finding devices, optical communications, and of course, barcode scanners. The unique characteristics of laser light make all these things possible. However, its use by eye surgeons to reattach retinas highlights them all. Injury can cause the eye's retina to peel away from the tissue supporting it. Without rapid treatment, the entire retina can become detached, causing blindness. Surgeons use green laser light of nearly a single wavelength because that color passes through the eye's lens and vitreous humor without being strongly absorbed, and thus without causing damage. The laser beam then strikes the retina where the tissue strongly absorbs that light, using the high-intensity light to weld the detached retina back into place. The beam's narrowness allows the surgeon to affect only the area of the retina that needs to be repaired, areas as small as 30 microns. How a laser creates light with these three characteristics is a tour de force of engineering. Let me show you. Any glow-in-the-dark toy can illustrate the basic principles of creating laser light. This glows because the zinc copper-based compound coating the inside can absorb energy from a light source and then later radiate it as light. The light provides energy to electrons in the coating, promoting them to higher energy levels. Once the light is off, these electrons slowly lose their added energy and return to their lower energy ground states. The energy lost is given off as light. A closely related phenomenon lies at the heart of a laser. Let me tell you about the engineering in the very first laser based on ruby. Here I have a tiny piece of ruby and some red colored glass beads. When I shine the blue light on the glass beads, nothing much happens, but shine it on the ruby and it glows red. Unlike the glow-in-the-dark ball, the light appears immediately, and when I shut off the blue light, it disappears. In 1960, Ted Mayman demonstrated the first laser by taking a cylinder of ruby and surrounding it with a xenon arc flash lamp used in aerial photography. An intense burst of light from the lamp initiates lasing. To see how it works, let's look at what happens with a weaker lamp. A flash would promote a few electrons from the ground state to an excited state. They'd lose a bit of energy, fall to a lower energy state without emitting light, and then drop from there to the ground state, giving off a burst of light. The light produced would be incoherent light, a spectrum of colors and intensities, just as my small laser made the ruby sphere glow. To create a laser takes an extremely powerful lamp. In the ruby laser, repeated flashes, called pumping, make something amazing happen. They supply so much energy that a population inversion occurs. Here, more electrons in the energy level just above the ground state than in the ground state. Electrons from a population inversion returning to the ground state release light that starts an avalanche called stimulated emission. The photon produced when an electron decays induces other excited electrons to simultaneously decay and release nearly identical photons. That creates coherent light, meaning that the crests and troughs of every light wave in the beam match up. Now, at this point, we have coherent light, but not yet the other two properties of laser light. To get a narrow beam with all the light rays parallel and of a nearly single wavelength requires an addition to the ruby rod. Mayman silvered the ends to reflect the light within the ruby cylinder. He made the two ends of the rod astonishingly parallel to each other. From top to bottom, the distance between these two mirrors differs by no more than 200 nanometers. Inside this resonant cavity, two things happen. First, any light rays that don't line up with the axis eventually just exit out the side of the cylinder, and the light parallel to the axis becomes intensified and narrowed in wavelength. The mirrored ends create a standing wave, which means only light of particular wavelengths can exist inside the cavity. By choosing the rod length correctly, we can get the nearly single wavelength of light characteristic of a laser. A small hole in one of the mirrors, or a partially silvered mirror, allows the light to escape, creating the familiar beam. Now, since the first ruby laser was created, lasers have become easy and cheap to manufacture. For instance, this laser pointer uses a semiconductor diode to produce light. Although many innovations and improvements have occurred since 1960, the essential principles are the same. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories. The chapter features more information about this subject. Learn more about the book at the address below.
My name is Mark Humphreys with Lincoln Electric Cutting Systems, and today we are showing the results of a return on investment case study that we performed using the Torchmate 4800. We compared the cost of outsourcing metal parts to be laser cut with the cost of bringing the manufacturing in-house through the purchase of a Torchmate cutting table. We're talking directly to the fabrication shops that outsource thousands of dollars a year in laser contracting, and we want to be completely open and honest about the cost savings that they can experience with the purchase of a Torchmate cutting table. For this study, we designed a couple parts that represented the simple metal shapes that the largest demographic of our customers could relate to: a simple flange and a tab cut out of 3/16 hot rolled mild steel. We took these designs and gave them to our local laser contractor with the condition that we needed 100 of each part every month. Then we cut out these parts using our brand new Torchmate table, and we compared the costs associated with each of these parts. For our calculations, we factored in many different variables that were associated with the cost of the metal parts coming off of the table, like the cost of the actual 4x8 metal sheet, how many parts we could fit onto that sheet, how long it would take to cut out, and how much money we would have to pay someone in order to operate the table. The most complex factor was the cost of consumables associated with the job. For this, we used the higher-end CAD software to calculate the amount of cut inches per part, and then we factored in hundreds of hours of test results on consumable life to predict the cost of consumables per foot of metal cut. The result was that we would need just under 2 4x8 metal sheets, that it would take a little less than 2.5 hours, and would go through just under 2 sets of consumables. This resulted in a 43% cost savings using the Torchmate 4800 over outsourcing those parts to be laser cut. This could be very lucrative for a business that is currently outsourcing parts to laser contractors. Let's say that you spend $2,000 in outsourcing a month, but decided to bring the manufacturing in-house with the purchase of a Torchmate table. Based on this model, you would save over $800 a month, and you wouldn't have to wait 3 weeks to get your parts back. Call a sales representative today to see if the quality and tolerances of plasma cutting are a good fit for your business.
This is my prototype Arduino laser rangefinder. It is very ugly and hastily put together, but it works. We have here a SparkFun Arduino Pro Mini, and on this side we have a little breakout board. This is one of our Arduino mini breakout boards, and it holds a Stonyman image sensor chip with a cell phone lens, and we see here a little transistor. What happens is that the Arduino is able to turn on and off the laser. The principle of operation is very simple. The laser turns on and off, and when the laser is off, the Arduino takes a picture. It basically grabs 3 rows of 32 pixels, not very many pixels, and then the laser is turned on and the Arduino grabs the same image, and then it just compares and sees which pixel changed in intensity, and that's the location of the laser point. Now in this video right now we have the laser turning on and off at a very slow rate. This is just to show you a video, but I can turn the speed up. So now there is about a 10 millisecond delay between when it turns off or turns on and when the image is grabbed. So first we'll start out at a very short range, and you can see right here at this very short distance, this is less than a foot, pixel number 2, pixel number 3 is being lit up. Using the geometry of the lens and the distance between the sensor and the laser, we can convert that to a distant measurement. But for now, I'm just going to tell you which pixel is lit up. So as I move away, pixel 6, pixel 7, 8, 9, 10, 11, 12, 13, 14 is lit up. 15, 16, 17, and you can see here by knowing which pixel is lit up, we can get an estimate of the distance. Now when I aim it at this corner over here, this is about 7 feet away, and pixel number 23 is lit up. At 14 feet, it's still detecting it. Pixel number 24 is lit up. Now if I shine the laser at this far away corner, this is about 26 feet away. Pixel number 24 is still lit up. What that means is that the disparity is basically the image sensor and the laser are not far apart to really be able to detect the change. The baseline needs to be larger, but at least we know that the laser can pick up. That the image sensor can pick up the laser at that distance. There are, of course, a number of ways we can improve this. We can increase the baseline, the distance between the image sensor and the laser, and that would let this work over a greater distance and allow us to resolve a greater distance. We could also use a telephoto lens. That would make the pixels closer together in the visual field, also increase the distance at which we can resolve different distances. We could use a brighter laser. That would extend the range a bit, of course at the cost of weight. We also have a little bandpass filter. I'm not using it here, but it's an optical bandpass filter that's tuned to let through just the laser light and block everything else. And what that would allow you to do is to use this in a brighter room. We've actually used this in a sunlit room. It doesn't work outside, but a bright sunlit room, it will work there. We can improve upon the analog signal quality, make the voltage regulator, use better voltage regulators and get a very clean analog signal. And finally, we can more tightly integrate everything. I bet you, using this laser module, which weighs about 1.9 grams, we can make the whole thing weigh maybe about 4 grams. Stay tuned.